Alright, this video is going to show you how to find the molecular structure, or it's also called molecular geometry, the shape of a one atom centered molecule using VSEPR theory. And VSEPR stands for Valence Shell Electron Pair Repulsion. And so what that means is that the electrons that surround the central atom are going to have to push against each other to where they get equal distances apart. And so it changes the shape depending on how many electrons you have around the central atom. Alright, I have tried to make this video 3 times now. I'm not going to be able to show any kind of 3D dimensional structure. I can just show what I've given you on a piece of paper in class, because everything that I've tried to use on the web, it doesn't show up on the screen right, and so it is pointless. So if you need extra help with this, seeing it 3-dimensionally, you can come in for tutorials, ask questions. I can try to find something for you to look at. There's also a really good website to use if you want to look them up, and it is called, I'll put it down here, it's called chemeddl.org, and you just click on resources and then go to Models 360. You can see all the structures in 3-dimensional space and rotate them around and see what they look like. All the ones in this presentation look the way they're supposed to. Some of the more advanced structures, especially stuff with sulfur and phosphorus in it, they'll look different from the way we discussed it in class, because we haven't gone through all of this. There's still more to learn on this, and we won't talk about it in pre-AP. We do talk about it, though, in AP Chemistry or any kind of dual credit class. Alright, so let's get started. Alright, so our first structure is going to be carbon dioxide, and in order to draw the structure, we have to count the number of valence electrons, and so carbon has 4, and oxygen has 6, but there's 2 of them, so that's 12 plus 4, so that's 16 valence electrons total. And so carbon is going to go in the middle, and then we're going to put the 2 oxygens on the outside. So right now we've got 2 4 electrons, 6, 8, 10, 12, 14, 16. So there's all the electrons that I can put out, and I have to check for the octet rule. This oxygen is good, this oxygen is good. This carbon only has 4 electrons around it, and it needs 8. So there's going to have to be some double bonding happening, so these 2 are going to come down like that. And so I would draw this structure like this. And now, in order to find the molecular geometry, or the shape of this, we're going to have to count the steric number. And the steric number is the number of different directions the electrons are arranged around the central atom. So carbon is our central atom, and the electrons are arranged in 2 different directions. They're arranged here, and they're arranged here. And so my steric number is 2. And then the second thing we have to check for is the number of lone pair of electrons. Now, a lone pair of electrons is just 2 paired electrons that are not involved in a bond. And so we're going to look at our central atom only, and this does not have any lone pair of electrons. Now, this oxygen has 2 lone pairs, but we're only looking at the central atom. So our central atom has no lone pairs. Alright, so now if I check the page that was given out in class so that you can find the correct geometry, we're going to look at that. And so that's right here. And so we have a steric number of 2 with 0 lone pairs, so here's a steric number 2, 0 lone pairs, and so the shape would be linear. As you can see, it makes a straight line here, and this is what it would look like. This is the best I got. It would be a straight line. So these would be the oxygens, and then that would be the carbon. Alright, so next we have H2CO, and so the first thing I have to do is count my number of valence electrons. And my number of valence electrons is going to be, hydrogen has 1 valence electron, so that's 2 times 1, plus 4 for carbon, and 6 for oxygen, so that's 12 valence electrons altogether. Hydrogen cannot be a central atom because it can only make one bond. It only has the one s orbital. It doesn't have a p, so it can't hold 8 electrons. So carbon will be my central atom. So I'm going to put carbon in the middle, and then I'm going to bond in my 2 hydrogens and my 1 oxygen. So I've used 2, 4, 6 electrons. Remember, each bond has 2 electrons in it. Okay, and so I've got 6 more to use. So I'm going to go on the outer atoms first. 2, 4, 6. And now I have to check my octet rule. Hydrogen, each hydrogen is good. It's got 2. And then oxygen has 8, so it's fine. But this carbon only has 6. And so this oxygen is going to have to share one of these pairs of electrons extra so that carbon stays happy. So it's going to look like this. And next I have to find my steric number. And my steric number is the number of different directions the electrons are arranged around the central atom. And so around this central atom I have 1, 2, 3 different directions. And then the lone pairs on my central atom, I don't have any lone pairs. There's 0 lone pairs on this carbon. So I'm going to check my sheet over here. And look at that. So I've got my steric number of 3 with 0 lone pairs, and so it's going to be trigonal planar. And it sits in a plane like this. So as you can see, there's nothing coming out of the top, there's nothing going down in the bottom, so it's just flat with 3 in a triangle shape. And that's why they call it trigonal planar. Okay. All right. Next we have nitrite. And so first I have to count my lone pairs, or I have to count my valence electrons. And so nitrogen has 5, and oxygen has 6, and there's 2 oxygens, so I'm going to multiply by 2. And then I have to add 1 because of this -1 charge. So that's 12 plus 1 is 13, plus 5 is 18 valence electrons. Now nitrogen is going to be my central atom, and I'm going to bond in the outer oxygens. So I've got 2, 4, 6, 8, 10, 12, 14, 16, and I have 2 more left, so I'm going to put it on the central atom. And now I have to check my octet rule. It's fine here, it's good there, but right here it needs 2 more electrons, so this oxygen is going to share an extra pair. So if I redraw this with my double bond, it will look like that. And since it's an ion, I'm going to put brackets around it and put my charge on the outside. Okay, so in order to find my shape, I have to count my steric number. And so remember, the steric number is just the number of different directions that the electrons are arranged around the central atom. And so they're arranged here's one direction, here's another, and here's another direction. And so that's 3 different directions that the electrons are arranged around the central atom. Now for lone pairs, I have this time 1 lone pair on my central atom, and so my lone pair is going to be 1. And so now I'm going to check my page over here and make this bigger so we can see it. Alright, and so if I have 3 as my steric number with 1 lone pair, then it's going to take on a bent shape. And the reason for that is these lone pair of electrons and this bond made of electrons, they're going to push each other to balanced positions because they don't want to be close to each other because both of them are negatively charged. So it's going to push these bonds down, and then these will be up here. And so it'll look bent because you can't see the electrons in space. All you can see is the atoms. And so we can tell by the way the atoms angle away from each other that this lone pair of electrons is up here. It bends these bonds down, and that's why we call it bent. And so the shape for this would be bent. Alright, next we have CH4, and so to count the valence electrons, we've got 4 for carbon, plus 4 times 1 for hydrogen, and that gives us 8. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Alright, so carbon is going to be the central atom, and then we've got 4 hydrogens to bond in. So that's going to be 2, 4, 6, 8 valence electrons, so they're all out there. Alright, and so next we have to find the steric number. And the steric number is going to be 1, 2, 3, 4 because the electrons are arranged in 4 different places around the central atom. And the number of lone pairs is going to be 0. So if we look over here, I've got a steric number of 4 with 0 lone pairs. That is going to be a tetrahedral shape. And so we can see here that this is, if we covered this thing in paper, it would have 4 different faces. And that's really hard to see on a flat plane, but you'd have one face here, you'd have one face on the bottom, one face over here, and then one face on this back piece. And so that's why they call it a tetrahedral, or a tetrahedron. Okay, so the shape for this would be tetrahedral. Alright, next we have NH3. So if I count my valence electrons, I've got 5 for nitrogen and 1 for each of the hydrogen, so that's 8 valence electrons. So nitrogen is going to go in the middle, and I've got 3 hydrogen, so that's 2, 4, 6 electrons, so I've got 2 more. They're going to go up there. And so I need to find my steric number next, and my steric number is going to be 4, and my number of lone pairs on my central atom is 1. So remember, these lone pairs count as a steric number. There's 1, 2, 3, 4 different directions the electrons are arranged around the central atom. And then we've got 1 lone pair. So if I look at my sheet, over here, I have a steric number of 4 with 0 lone pairs. And so my shape, a steric number of 4 with 1 lone pair, and so it's going to be trigonal pyramid. And so in this one, we've got these 3 that go out like this, but then this lone pair forces these bonds down into a pyramid shape. And so it ends up looking like that. So this lone pair of electrons that are over here on this force these bonds down and away from it because it's called valence shell electron pair repulsion. And so it turns it into a pyramid shape. So the shape of this one is called trigonal pyramid. And you have to be able to differentiate between trigonal pyramid and trigonal planar. Remember, trigonal planar is flat. If there was a lone pair up here, it'd force these bonds down into a pyramid position. All right, next we have water. And so to count the number of valence electrons, we have 1 for each of the hydrogen, plus the 6 from oxygen, and so that's 8 valence electrons. Oxygen will go in the middle, and then we'll bond the hydrogens in. And so I have 2, 4, and then I have to put the rest of the electrons on the central atom, 6, 8, because I can't put any more on hydrogen. Hydrogen can only make a bond, that's all it can do. And so now if I count my steric number, it has a steric number of 4 with 2 lone pairs, right? So the electrons are arranged in 1, 2, 3, 4 different directions, and then has 2 lone pairs. And so if I'm going to check the geometry of it, I'll look over here, and I've got a steric number of 4 with 2 lone pairs. And so this is one also is going to be bent, because if these two were laying out flat and had these lone pairs up here, it would force these bonds down. And so it takes on this bent-like structure. And you can see over here on this side, whoa, what that would look like. Okay, so the lone pairs are actually coming out this way and going back into the screen that way. All right, so yeah, I hope that you're catching on of how to find it on using this page. All right, PF5, phosphorus has got 5 valence electrons. Fluorine has 7, and there's 5 of them, so that's going to be 35 plus 5, or 40 valence electrons. So we're going to put phosphorus in the middle, and 5 fluorines around it. Okay, and so right now we've used 2, 4, 6, 8, 10 electrons. So there's 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So there's 40 valence electrons. Everything is out. Phosphorus can go past the octet because it's in the third period of the periodic table. So anything in the third period or lower can go past the octet rule because they have the empty D shell they can put electrons in. They don't have to hold more than 8, but they can. All right, so looking for my steric number. My steric number here is going to be 1, 2, 3, 4, and 5. And then my number of lone pairs on the central atom is 0. So if I look at my page over here, then 5 and 0 is going to be trigonal bipyramidal. And this one is also difficult to see on a flat piece of paper, but this X goes back into the screen, and this X comes out of the screen. So there's a triangle where this side is digging into the screen, and this side is coming out at you. And so you have a trigonal pyramid on the top, and then you also have a trigonal pyramid on the bottom. And so that's why they call it trigonal bipyramidal, because it's 2 pyramids. So you can see this pyramid right here, and then my screenshot, I had that on there, and I didn't notice it. And this video is taking too long as it is, so I just left it. But the shape is going to be trigonal bipyramidal, and so that's what you would write. You'd write trigonal bipyramidal, or bipyramid. All right, so if you have 5 bonded atoms to a central atom, it's going to be trigonal bipyramidal. All right, it's just a couple more now. So we've got sulfur tetrafluoride here, and so sulfur has 6 valence electrons, fluorine has 7, and there's 4 of them. So 28 plus 6 is going to be 34 electrons, and sulfur will be in the middle, and we'll bond in 4 fluorines. And so right now I've got 2, 4, 6, 8, and then 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 2 more electrons left over. Those have to go on the central atom, like that. Okay, and so to find the steric number for this, the electrons are arranged in 1, 2, 3, 4, 5 different places, different directions, and the number of lone pairs is 1. So with this one, we look over here, and with a steric number of 5 with 1 lone pair, it's going to be seesaw. And so it makes a little seesaw, right? This side goes down, this side goes up, then this side goes down, then that side goes up. And so that's why they call it seesaw. And so there's the 1 lone pair of electrons that would be sticking up out here if you could see it. All right, and it keeps these at this shape. Otherwise, this would come up. And this one would too. All right, let's do a couple more. So I've got chlorine trifluoride. Chlorine has 7 valence electrons. Fluorine has 7 too, but there's 3 of them, so 21 plus 7 is 28 valence electrons. Chlorine will go in the middle, and then I'll have 3 fluorines. All right, and so right now I've got 2, 4, 6 electrons. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. Oh, I made that a carbon. That needs to be a chlorine. Okay, so chlorine is in the third period, so it can go past the octet rule, so this is fine. For the steric number for chlorine, I'm going to have 1, 2, 3, 4, 5. And then for the number of lone pairs, there will be 2. So now I need to check my page. Whoa, what's that? I need to check my page over here. Okay, and so I've got 5 is my steric number, 2 lone pairs, and so this is going to be T-shaped. It looks just like a T. Alright, and so this pair of electrons is coming out of the screen, and that pair of electrons is going into the screen, so it comes out over here and then back over there. And so it'll look T-shaped, and so that's what we would write, would be T-shaped. Alright, 2 more. So this is triiodide. So to find the number of electrons, it's going to be 3 times 7 plus 1 for the negative charge. So that's 22 valence electrons. And so I've got iodine with 2 more iodines. So there's 2, 4 electrons, 6, 8, 10, 12, 14, 16, 18, 20, and 22. And my steric number for the central iodine is 1, 2, 3, 4, 5. And for my number of lone pairs, I've got 1, 2, and 3 lone pairs. And so if I wanted to check and see what the shape was, then I would just look over here. And so with a steric number of 5, with 3 lone pairs, the shape is linear again because these come off, right? Or they don't come off, but they're not there. You can't see them. And so they hold this at a linear position. All right, and so my shape is linear. All right, last one, SF6. So sulfur has 6 valence electrons plus 6 times 7 for each fluorine, so that's 48 valence electrons. Sulfur goes in the middle, and we've got 6 fluorines. So right now there's 2, 4, 6, 8, 10, 12 electrons. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So there's all the valence electrons. My steric number for this is 6, and my number of lone pairs is 0. And so if I wanted to find my shape for this, then I would just look over here, right? And so with 6 and 0, the shape is going to be octahedral. And so you can see here, looking at this structure, there's a square right here, right? And these 2 are in the back, and these 2 are coming out of the screen. So there's one face here, one face here, one face there, one face in the back, and then the same thing on the bottom. And so this shape has 8 faces, and that's why they call it octahedral. So if you had to determine, what the shape was, you would write octahedral for this. Alright, that's it. That's all the shapes that I've come up with for this video. I hope this helped. If you still need help, come in and get it. Or use that website that I gave you in the beginning and look these shapes up. It will help you understand what they look like in 3D space. Alright, good luck.